quantum computing actually. This will focus on the aspects you need to know in order to program a quantum computer. So I will really concentrate on the things you need to know to write a small program for a quantum computer. I will not go into the physics or how to build a quantum computer actually, even though that's of course also very interesting, especially for the physicists here. But I will not go into that. The first exercise, then we will write a small quantum program or quantum circuit with Qiskit. And then I will walk you through Deutsche Algorithm. Deutsche Algorithm was one of the first algorithms invented, which proved that quantum computers for some tasks can be superior to classical computers. So it's interesting from a historical perspective, but also because it's relatively easy to understand and implement. And that's what we are going to do then. We will implement Deutsche Algorithm. And finally, I will give some outlook on the current state of quantum computing and some further resources if you are interested to follow up on this topic. I have to say, I'm not entirely sure we will make it through my program here. It's the first time I'm teaching this, and also it's not always easy to explain. And for me, it's more important that in case you have any issues or questions, that you really put them into the chat and ask, and that we try to get the vast majority of you along instead of finishing this and losing most of you, even though I try to use examples which are understandable without previous knowledge. So let's restate what we want to learn today. We want to learn to formulate small quantum algorithms as quantum circuits, which are quantum programs. We want to implement such small quantum circuits. And finally, we want to understand and implement Deutsche Algorithm for quantum computers. Okay, without further ado, as I said, if you have any questions, just post them in the chat. I try to follow there. You can also try to raise your hand, but I'm not sure if I'm seeing that, so probably it's better to just put something into the chat. Okay, let's start. And as always, one should do, let's start small. And the smallest unit of information in quantum computing is actually the qubit. Qubit stands for quantum bit, basically, and it's similar to the classical bit in that way that it can have the states 0 and 1. It can also have other states, but we will get back to that later. However, the qubit is represented as a two-dimensional vector. So we write the 0 state of the qubit as a vector 1, 0, and we write the 1 state of the qubit as a vector 0, 1, which is orthogonal to the other vector, by the way. If we, I should also briefly say something about this notation here with angle bracket and this line here. It's called a cat from Bra cat notation. You don't need to know more about this than that when we write this, we actually mean this vector here. That's all you need. It's a shorthand for this vector, state vector. So as long as you only use the 0 and 1 states of a qubit, calculations or computations with these states are very similar to classical computing. There's not really much different about them. Okay, so let's try to do something with our qubit. One thing we can do with single qubit is to negate it, so to apply a NOT to the qubit. And such operations on a qubit are called gates, similar to the logic gates where you also have a NOT gate in classical computing. However, as our qubits, as I said, are vectors, when we want to transform them into another vector, we can write that down as a matrix. It's somewhat similar to what you know maybe from 3D graphics, where your objects in 3D space are represented by vectors, where you can then apply deformations, transformations, rotations, etc. to transform your 3D objects. And here we use matrices to transform our state vectors into another state vector. So let's try to do this with the NOT gate, also called X gate in quantum computing. let's take the 0 state and apply the NOT gate, which is written as this matrix here. And then you can do a simple matrix vector multiplication. So you multiply 0 by 1, 1 by 0, and add this together to receive 0. And again, you multiply 1 by 1 and 0 by 0, add that together, and you apply 1. You get 1. Yeah, that's actually our 1 state, as described on the previous slide. So that's all there's to do to apply the NOT to our qubit. As a brief exercise, maybe for a few seconds, just do the same thing and apply this matrix to the 1 vector, which would be 0, 1, and see that you get 0 out of it. I'll wait a few seconds until you have done that on the paper or in your head, as you like. Okay, it's working for you. Okay. So I hope all of you convinced yourselves that indeed, if you apply this matrix to the 1 vector, you get 1, 0 here, and that's the 0 state. Yeah, that's working for you. Okay. Now we know what the qubit is and how to transform it into a different state. We have seen that for the NOT gate. Now we want to see how we can formulate this into a quantum program. And the most important programming paradigm for quantum computers right now are quantum circuits. And they are written up like this one, like this little picture here, which probably reminds you a little bit of a music sheet, for example, and there are actually some similarities. So your qubit starts on the left-hand side, usually in a computational basis state. I forgot to mention that name. That's the name for the 2 possible states, for the 2 states 0 and 1. So it starts as a 0 or 1 here. And then it's represented by this line here, which we call a quantum wire. And on the quantum wire, you can then place operations. For example, in this case, we've played an X gate here, which we know from the previous slide, which applies not to our quantum, to our qubit. And then it continues along this line. We can place additional operations and or gates, obviously. But what we do here finally is doing a measurement. The measurement ends your quantum circuit and transforms the qubit state into a classical bit. By this transformation, you can only read out 0 or 1 states from the qubit. So we call it a measurement in the computational basis. You cannot get any other state out of it. Okay, so now we know what the qubit is, how to transform it by gates, and how to place gates and a measurement onto a quantum circuit, where we see our quantum, our qubit as a quantum wire, and we can continue from this. Everything clear so far? No questions? Everyone could follow? Very good. Okay. Now, up to now, we have only talked about the 2 computational basis states, 0 and 1. But that wouldn't make quantum computing very powerful, obviously. So say hello to another gate or operation, which is called the Hadamard or H gate. And this does something different to our qubit now. It's represented by this matrix here. And you can ignore for now the 1 over square root 2 here. That's that I explain later. And what it does, you can actually see from the matrix. If you look at such a 2-column matrix for qubit gates, the left-hand side will always tell you, or the left column will always tell you what happens to the 0 state, and the right-hand side will tell you what happens to the 1 state. You can see this also on the previous slide. Here, for the NOT gate, you see the 0 state will land at 0, 1, which is the 1 state, and the 1 state will be at 1, 0 after the transformation, which is the 0 state. Okay, so for the Hadamard gate, we can say that for the 0 state will land at 1, 1, and the 1 state will land at 1, minus 1. I've written this out here. So after the operation of the Hadamard gate, our 0 state here will be in the state 1, 1. Using the rules for vector addition, we can also write this as 1, 0 plus 0, 1, which is in fact just, again, our basis state vectors 0 and 1. So what happens is that the Hadamard gate puts our qubit into a linear combination of the two basis states, which we also call a superposition. As a brief exercise, you could try to apply this matrix operation to the 0, 1 state, which is to the 0, 1 vector, which is the 1 state, and receive this result. It's probably good thing to do right now in order to see that this works out as expected. I'll wait a couple of seconds. Okay, I hope you convinced yourselves that this works out. One more thing we should know about the Hadamard gate is that it's its own inverse. That's the same also for the NOT gate. And it means that when we apply it twice, it returns the original result. So applying the Hadamard gate to the 1, 1 vector here yields again the 0 state from which we produced it up here. And applying the Hadamard gate to the 1, minus 1 vector yields the 1 state again, which we received from the application to the 1 state. If you like, you can check that as well. Okay, now let's build the Hadamard gate into a quantum circuit. As I explained, we start out with qubit in state 0. Then we apply the NOT gate here, or the X gate, and transform it to the 1 state. And then we apply the Hadamard gate to get the 1, minus 1 mixed state, as shown on the previous slide. Finally, we measure this one, and the question is, what do we get now? As I said, we can only measure the qubits in our computational basis, so we cannot get this mixed state here. We can only get 0 or 1. And so what we will receive is either 0 or 1, and if you measure several times, it turns out that they are of equal probability. So you will get 50% the 0 state and 50% the 1 state. It turns out that this is a general rule. For any superposition, for any valid superposition, which represents a state of your qubit with coefficients A and B, when they are real coefficient, the probability to measure the qubit in the 0 state will be equal to A squared, and the probability to measure it in the 1 state will be equal to B squared. Actually, A and B can be complex numbers, so I should work with the values squared. But for today, we don't concern ourselves with any complex coefficients, even though, of course, it's an additional degree of freedom, which is important for many algorithms, but not for the algorithms we will look at today. This here is basically also Schrödinger's cat, right? Because if you have your basis states for the cat, which would be living and dead. I mean, you probably all have heard of Schrödinger's cat. So the basis state would be living and dead, and you would apply Hadamard gate. It would be in a mixed state of living and dead. And once you measure it, it would be either living or dead, the poor thing. And it also would stay that way. And that's also true for all of our qubits. Once we measure it, and we have gotten 0 or 1 here, if we measure it again, it will stay in that state. It's no longer a mixed state. So if you measure it repeatedly, it will always give the same result as the first time. Okay. Is that clear so far? No, it's quite a bit. No questions? Feel free. It's not bad to ask questions. I know it's sometimes hard to explain this stuff. Okay. Good. Then let's continue. Let's get to multiple qubits. Just one qubit doesn't get us very far. So yeah, we need more qubits actually. And if you combine 2 qubits, you have to use a tensor product of the 2 qubit state in order to get a new state of the 2 qubits. I won't go into tensor products here. That would be a bit too much. Just a simple version which we need here would be that you take the upper value of the left-hand vector and multiply it by the right-hand vector and put that on top. And then you take the lower value of the left-hand vector and multiply it with the vector again and put that at the bottom. And then you get a 4 vector of the combined state of the 2 qubits. And again, you can write that out into basis functions where you use the cat writing in order to represent the basis functions. And those are the 0, 0 state, the 0, 1 state, the 1, 0 state, and the 1, 1 state, just as you count with bits usually. And they all have a coefficient. And again, if you have a mixed state of these computational basis for 2 qubits, they have to add up to 1. I didn't explain that. Why do they have to add up to 1? The reason is, of course, that to find the qubit in any state, the probability is 1. So it cannot be higher or lower. You know all states, you know all coefficients. So they have to add up to 1 in order to represent the probabilities to find the qubit in any state. Okay. Let's do a small example. 1 qubit in the 0 state, 1 qubit in the 1 state. So you have one times the 1 state up here, and you have 0 times the 1 state down here. So in all, this gives the second coefficient here, 100%. Your 2 qubit system will be in the 0, 1 state, just as you would expect from a classical system, right? If you have a 0 and a 1. And 0 is the higher valued bit. You can extend this. For every qubit you add, you do this again. So you double the amount of the dimensionality of your vector and get according more possible states. This grows exponentially, of course, with the number of qubits. And it turns out that only up to 30-something qubits you can simulate classically. And otherwise, that would be kind of a bad thing, because then quantum computing would not be very useful if you could just simulate it on a classical computer. What does combine mean? Combining qubit states. Yeah, that's just basically it's building the tensor product of two qubits, which is kind of a circular argument. What I mean is you have to describe 2 qubits together. As we see later, for example, when we speak about entanglement, you will see that you cannot view the 2 qubits independently. So you have to combine the 2 qubit state into a single state description, basically, and that's what I mean. Compared to classically is a real quantum computer. It does not seem to be a full sentence. Yes, 0, 1 is not, no, 0, 1 is a combined state of the of two qubits, where the first qubit is in 0 state and the second qubit is in 1 state. Right? That's what we did here, basically. We have the first qubit in the 0 state, the second qubit in the 1 state, and when we do the tensor product, we get this new vector with 100% probability in this coefficient. This is the coefficient for 0, 1. And so we know our 2 qubit is in 0, 1 state. And the 0, 1 state means basically one qubit is in the 0 state and the other is in the 1 state. No, it's not an entangled state because you can separate it, right? It's what we did here. You can easily separate it and write it as I did here, as the normal tensor product of the two basis states for the single qubit. So it's not entangled. Maybe that becomes clearer once we get to entangled state. Okay. Good. I'm not sure if there's questions coming. That's the reason I'm waiting a bit here. Still people typing. Okay, maybe I continue for now and look at the chat in a couple of seconds. Good, now that we have 2 qubits, we can use 2 qubit gates. That's a good thing. And the first 2 qubit gate we want to use is a C0 or XOR gate. And in a quantum circuit, it is written like this, with the dot here and the sign for the NOT gate here, connected by a line. That's the reason for one possible, and the reason for this is one possible definition of the C0 gate. And that definition is, if the qubit with the dot here, which is called the control qubit, like in C0, which stands for control NOT, is 1, then apply a NOT to the other qubit. So if you begin with the state 0, 1, where this would be 1, this would be switched to 1, 1. Okay, so whenever 1 goes through here, this one is switched either from 0 to 1 or from 1 to 0. If this is 0, nothing happens here. That's one way to look at the C0 gate. The other way is to see it as an XOR, and that becomes clear when you look at both qubits as input value and Q1 as the output value. In that case, if both are 1, then this here will be switched back to 0, which is the expected result for 1 XOR 1. If both are 0, then nothing will happen. And again, this will be 0, like in the XOR expectation. If it is 0, 1, then this will be 1 and switch this also to 1, which is also the expected value for XOR 0 and 1. So that's the second definition of the XOR gate. You can also just look again at the matrix representation and remember that you can use the columns to see where the corresponding basis vectors will land. And this here is 0, 0, this here is 0, 1, this here is 1, 0, this here is 1, 1. So you see the 1, 0 will land at 1, 1. And the 1, 1 will land at 0, 1. I've also written it here. So A0, 0, the coefficient stays the same. A01 becomes A11, A10 stays the same, A11 becomes A01. That's also clear if you remember, the white one is the control qubit. So if you enter 01 here, the white one will switch the 0 here to 1 and you get A11, and same here, other way around. So that's the different definitions or ways to look at the XOR or CNOT gate. I should mention here that in difference to many textbook, the Qiskit system, which we use later to program, uses a qubit order starting from top with the rightmost qubit. So in this notation, this here would be Q0, this here would be Q1. That means if you have a state of 0, 1, that means this one is 0. 0, 1 would mean this one is 0 and this one is 1. Bit confusing sometimes if you read other textbook who do it the other way around. One more thing, quantum gates need to be reversible. What does that mean? You need to always have an inverse of your gate which produces again the state which you had before applying the gate. And that means that you cannot have the classical 2-bit gates where you combine two values into one. For example, the classical XOR gate would have two values entering and one value going out with the result. But this would lose information and therefore you could not reverse it with an inverse. That is not allowed quantum gate. All quantum gates need to be reversible. That's the reason for that being that physics controls this basically. Okay. Any questions so far? Clear how the CNOT gate works, how it in the end simply exchanges these two values. Of course, it looks at the right value and changes the first the left value if the right value is 1. So it doesn't do anything here, it doesn't do anything here, but it switches basically these two values to old NOT gate. Okay, good. Now, let's talk about entanglement. Let's consider this quantum circuit. Let's first apply the Hadamard gate in order to get the Q0 qubit into a mixed state, and then apply the CNOT, where we use the mixed state as a control and the other qubit as a target, and then we measure both. What we get out of this is that for each qubit, you get 50% chance to measure it in 1 or in 0. But if you measure one qubit in 0, you are certain to measure the other qubit in 0 as well. And the other way around. If you measure one qubit in 1, the other will be 100% certain also be 1. This is called entanglement. It's famous for Einstein's words about spooky actions as a distance, because basically after you have entangled the qubit here, you can separate them by any distance and measure them at the same time. You have to coordinate that somewhere how it's done experimentally. If you measure them at the same time, they will auto-magically result in the same value. And Einstein wouldn't accept that this is possible because you are basically limited by light speed when transmitting information. But in the end, no transfer when you transfer information. But in this case, no information is really transferred. You cannot use this to fax something to someone else because there's no way of knowing what you will measure beforehand, right? You will know once you have measured that you have measured the same thing, but you cannot know what you will measure beforehand. So it's not possible to transmit any information using this. Mathematically, it's actually very simple. Let's first start with the application of the Hadamard gate. I've written it here as identity tensor product Hadamard. The reason simply being that I have to write something which I do to the Q1 qubit. and identity simply means I won't change anything. So it's basically just Hadamard to the 0 qubit. If I do that to the 0, 0 state, I get a linear combination of the 0, 0 or superposition of the 0, 0 and the 0, 1 state, because the lower valued qubit, Q0, is now in a superposition of 0 and 1. So I get these two states combined. Then I apply the C0 gate. The C0 gate doesn't anything to this state here because the control qubit is 0. But here the control qubit is 1. And so I switch this one also to 1, and I get this state 0, 0 plus 1, 1. Okay, and that's entanglement. It's basically all. Now we know that we have a state in which both qubits have to agree on their state, but can still have any of both their computational basis states. Okay. What does plus mean? Just a vector addition, or I separated basically my vector. I'll show it once more. Here you can see it. If I have a vector 1, 1, right, I can write it as the vector 1, 0 plus 0, 1, because that's simple vector addition, right? I can always add up the rows of two vectors, which this is what the plus sign basically says. Okay. More questions? Yeah, well, I wouldn't worry about it, but about those circles. But good. More questions? Everyone's clear about what spooky action at a distance is. It's just really very simple application of qubits, of gates to qubits. Good. Then, just in time, we can start with the first exercise, actually. I hope all of you have downloaded and placed the code and install script from from the website in your directory, in your home directory at the SCC. Then you can execute source the shell script provided in order to install Qiskit. Of course, if you know some shell scripting already from the previous lectures, you can also look into the installation script and do what you think is needed. But that's what you should do now first. And before you do the rest, let me first show you what is inside the file xbase Python. Okay, can you see my screen? Hope you can. Good. Think. Okay. Good. So Qiskit, what's Qiskit? In a few words, it's a programming environment by IBM for programming quantum computers. It basically consists of a library by which we can easily construct quantum circuits. Then there is transpiler, which is a fancy word for compiler, which compiles your quantum circuits in runnable programs, either for a quantum computer, for a real quantum computer, or for a simulator. And Qiskit also contains such simulators in order to run a quantum circuit if you have no quantum computer around. Yeah, well, no, those simulators can get complicated, I'd say, because they also can simulate noise and etc. Yeah, I don't want to get too much into this today, actually. Let's rather just look at the skeleton I provided for the exercises. Okay, there's some imports obviously done from Qiskit. We import the quantum circuit and transpiler for this. We import a simulator, and we import also something to visualize. Then first thing is we define the simulator. Second thing is we define a quantum circuit here of size 2 qubits. So the argument for quantum circuits is just the number of 2 qubits in this case. And then we can put gates into our quantum circuit. So here I put an H gate onto qubit 0 and an H gate onto qubit 1. That's all. Then we do the measurement. In this case, we don't say, we just measure all qubits. Then we use the provided library in order to draw our quantum circuit. And finally, we will transpile it for our simulator, run the jobs 1,000 times, get the results from the job, get the counts of the results, and plot them in a histogram. That's basically it. So let me execute this. So as you can see here, this is a quantum circuit like we have drawn it on our slides before. Here are the two Hadamard gates, qubit 0, qubit 1. The quantum wire starts, two Hadamard gates, two measurements, and this is the result. So we have a more or less even distribution of the four states 0, 0, 0, 1, 1, 0, 1, 1. Okay? Good. Now, what's to do in the exercise? First, install Qiskit. Probably you have already started. Then run X-Base Python. Take a look at the result and think a bit about it if it's what you expected. You could try to write it down as a corresponding superposition in terms of the basis states I mentioned, 0, 0, 0, 1, 1, 1, 0, 1, 1. I mean, I've said already it's an equal distribution. You just have to think about the factor, of course, in order that it all adds up to 1 when you take the squared coefficient. Yeah, and that's basically all. Now, in the next step, entangle the 2 qubits. Instead of like I did it before with the Hadamard and the C0 gate, use an X gate in order to, in addition, before you entangle. And take a look at the result of your entangled qubit measurement and think about if it's what you expected or if you would have expected something else and why or why not. Yeah, that's basically the main task. However, because some of you won't take long for that, I guess, I have some additional optional tasks. 1A would be, we now discuss the entangled state of 0, 0 and 1, 1, but there's also an entangled state of 0, 1 and 1, 0. So that's the state where the 2 qubits are certain to disagree, right? So I measure 1 in 0, then I know the other one will be in state 1. And you implement a quantum circuit which produces this state. Hint, I've written it here, you only need one additional gate, and you probably should just think in terms of how you can manipulate the original vector here, so that the exchange of these two terms in the end results on zero probability for A00, A11, and non-zero probability for these two states. Think a bit about it, it's probably easier than you think right now. The other thing you could do is to produce a Tangle state of 4 qubits. So create a circuit with 4 qubits and try to get it in a state where they can only be all in agreement, either agree on to be in the 0 state or agree on the 1 state. For this, you need to produce a bigger circle with 4 qubits. And yeah, as a hint, start just by entangling as before with 2 qubits. After that, the first 3 of your now 4 qubits will be in the state 0, 0 plus 1, 1 for the first 2 qubits, and the third qubit will be in the 0 state, right? And if you look at that, you see that you just want to switch this one, 1, 1, 0 to 1, 1, 1, but not this one, 0, 0, 0 to 1, 0, 0. What gate does this? You don't have that many options actually on gates which are doing this. And yeah, one of them is the right one. Okay, very good. I would say as the 2 tasks here are optional, we use 15 minutes for this task. Would that be okay? And meet again, so 5 after 5 or a little bit later, 1 or 2 minutes later. Okay? So, everyone, please try this out. I hope you find some success. I will go around in 1 or 2 minutes to the breakout rooms and see how we are doing. Yeah, and then let's meet 5 after 5 again here. Have fun. Okay. Yeah, thanks, Tino. You put an X gate on 0, then the Hadamard on 0, then X gate on 1. Yeah, yeah. That's the right solution for the other entangled state, correct? Very good. Okay. I actually did not prepare a solution for the first slide. I thought that would not be necessary. Okay, maybe I just explain the first solution. Good. Yeah, the first thing here was anyway just to run XBase, which I can do here. Okay, and the result is that we have an equal distribution across the 4 2-qubit states, and that's also what we would expect because we have no entanglement here. We just applied separately the Hadamard gate, and so both the qubits are in a mixed state, and we get all 4 possible combined state with equal probability. And also, if you want to express this in terms of the basis states, you just have the equal probability there. So this would be 1 factor times 0, 0, and then the factor times 0, 1, and so on. And now the question is only what's the correct factor, and that's 1/2, because if you square 1/2, it gives 1/4, and you have 4 probabilities of 1/4 each. And that means that's the right way to express the state. So it's 1/2, 0, 0, plus 1/2, 0, 1, plus 1/2, 1, 0, plus 1/2, 1, 1. That's the state which we get with this circuit here. Okay, now I see. Good. The next task is we entangle the qubits. We did basically the same as we did before. Just we added this X gate before applying the other MAT gate. So when we apply the other MAT gate, we do not get the 0 plus 1 state, but the 0 minus 1 state. But the result in the probabilities is the same as before. And the reason for that is, of course, that if you square the negative probability, if you square the negative coefficient in order to get the probability is the same, because in the square, of course, the minus sign vanishes. And so, yeah, that's the same result independently if you use this X gate or not. This negative sign is also called the phase of the state, and we will make use of it later. Okay. The input is always, we always start our quantum circuit with both qubits in the 0 state, right? They always start in the 0 state, and then they change state with the first gates we give it. So that's the general rule. Always start with the 0 state, then apply a few gates, and in the end, do a measurement in the basis states, which either gives 0 or 1 states. Good, so much for the solution of the first slide. Now get to the second slide. For this, I need to really share my screen. So, by the way, this is again the screen. This here again is the equally distributed state with the 2 Hadamard gates, as I said, each equal distribution. Okay, now let's do the Bell state, the 0, 1, 1, 0 state, which is called a Bell state, but that's not so important now. This time I use more fancy matplotlib drawing of the circuit, so I have to move from window. But it's a solution which was it Tino? Yeah, Tino, you also mentioned. So in order to get this state 0, 1 plus 1, 0, you have to apply an X gate in addition to our usual way of getting the entangled state. And then it gives this one, and you can actually see this again from our state vector, because if you apply the X gate first, you basically get a mixture of the 1, 0 and the 0. On top of my mind, you get a mixture of the 1, 1 and the 1, 0 state, and then you change the 1, 1 for the 0, 1 state, and then it's exactly what you get here. Right? Okay, yeah, good solution. Now, did anyone solve the final task with the GHZ state, where you entangle 4 qubits? Okay. I thought that might be a bit difficult actually, but let me show. So the idea is really to propagate basically this exchanges of states, which the C0 does, further down the qubit circle. So you just entangle the first two qubits, then you entangle the next two qubits, and then you entangle the final qubit. And the same thing would basically happen if you always use the first qubit for entanglement. So you could also, instead of doing Q1, Q0, Q1, Q1, Q2, you could also do Q0, Q1, Q0, Q2, and Q0, Q3. That would also be a valid solution. You can try it out if you want. It's the same result. I'm not sure if this is an error correction code valid. I don't think so, no. For error correction, you usually want to have states which basically are robust to changes of one qubit. I'm not sure right now, I have to admit. Maybe I'm missing something. Good. Further questions? Solutions clear? Okay. No questions. Then let's get to a little bit more math. I hope I don't overwhelm you in order to understand Deutsch's problem before we can all go to dinner. So, as I mentioned in the introduction, Deutsch was in the 90s one of the first persons who actually proved that a quantum computer could be superior to a classical computer. And he did it with a simple but rather artificial problem. And the problem is this. Think you would have a function of 1 bit, right? There's basically 4 things you can do to a bit. You can set it constantly to 1, you can set it constantly to 0, you can keep it as it was, so 0 stays 0 and 1 stays 1, or you can negate it with not, right? So then 0 becomes 1 and 1 becomes 0. So if you want to test which function you have, you need basically 2 tries, right? And you need 2 tries in the quantum case and in the classical case. I don't want to get into that because the problem which Deutsch made out of this is a bit different. He just wanted to know if the result is a constant function. So constant would be constant 0 and constant 1, right? Or if it is a balance, which gives different results for each input. So that would be identity, which gives 0 for 0 and 1 for 1, and negation, which would give 1 for 0 and 0 for 1. So we wanted to decide if it's a constant function or one which depends on the input and is therefore balanced. Classically, you still need to do 2 tries to find out what it is, because if you supply a 0 to the function and you get a 0, you don't know if it's the identity or constant 0, right? So we have to supply 0 again. You have to supply 1 in order to know if it's now again 0 or becomes 1, in which case it would be the identity. Clear so far what the problem is which Deutsch tried to describe? Okay, now let's try to, what Deutsch tried was to put this into a quantum circuit. So he said there should be a gate which applies our function to 2 qubits. Please remember from when I introduced the X0 as a C0 gate that quantum gates must be reversible. So for 2 incoming qubits, we need 2 outcoming qubits. We cannot just give only the result. And so in Deutsch formulation of this problem, the Q0 is the input qubit and Q1 is the output qubit. Okay? That's the only difference to the classical formulation up to now. mathematically, you can write this now as this. If x is our input and y is our output, our gate UF will transform this. It will leave the input qubit x unchanged, of course, because it's the input, and it will change the output. Because we usually have all qubits started as 0, you could just write then just write the function result of the function into this bit, into this qubit, right? So if x is 0 and you have constant 1, you would write a 1 into this one. However, because we can set basically our output qubit to anything we want, we give it a more general description, and that is we take whatever is in the output qubit, it's usually 0, add the function result. In the case it's 0, then you have, as before, just the function result, and apply modulo 2. That is what's written here. So in the case that you have provided 1 for the output before, and the result is 1, you get again 0 here. Okay? So that's the change we do here to the formulation of the problem. So the result from application of our gate to the state of x, y is x and y plus the function result modulo 2. Okay. Now we have our problem described as a quantum state. Oh, it's quantum algorithm. Now the idea was of Deutsch to cheat. Instead of using 0 for the output, we could use mixed state. This is a mixed state we get from applying Hadamard to the 1 state, right? It's a 0 minus 1, which we saw before. Let's just put this into our quantum circuit. What happens? Okay, we now apply our gate, our UF gate, to x and y in the state, as I have written here, 1 over square root 2, 0, minus 1. Okay, when we apply the UF gate, x remains unchanged, of course, it's the input. But for y, we now get, or for the Q1 qubit, where we want to store our output, we now get f on x if it's 0, right? So we can, instead of the 0 state here, write f on x as state minus 1 plus f on x. This is again this plus z modulo 2, because in that case, this modulo 2 becomes important, right? Because we have already 1 in the y variable, or in the second qubit. Okay, now let's look at this. If the result of, or if f on x is 0, then this is again the 0 state minus the 1 state, because then this part is also 0, so this is just again 0 minus 1, which was our original function. So let's write this here. If, on the other hand, the function result is 1, then this is 1 minus 0, because 1 plus 1 modulo 2 is 0, right? So this is 1 minus 0. 1 minus 0 again is just minus 1 times 0 minus 1. We can minus 1 to the front of all our stuff here. We move it here. Okay. To the power of f on x, of f of x. Because if f of x is 0, then this is just times 1, this function times 1. And if f of x is 1, this is minus 1 times this part here, which is exactly what we have written here. Okay? Can you follow? Questions? Too bad that you can't follow. Can I help somehow? Don't let the many parentheses and stuff confused you. It's really just, okay, yeah, Martin, maybe, but it's really just saying basically we write the fact that we can have this part -1 or not, depending on the function result, as -1 to the power of the function result, right? Because -1 to the power of 0 is 1, and -1 to the power of 1 is -1. So it's just saying this can be either -1 times this or 1 times this. Okay, that's basically all that is about it. Okay, but the tricky thing or the good thing about what we have done here now is that by doing this, we have basically left the output qubit unchanged. This is exactly what we did used as the output qubit, but we have managed to get a factor here, depending on the function results, to the input qubit. That's a great thing, and it's used in many quantum algorithms. Because the sign is related to the phase of the qubit, we don't talk about phases here, but let's just take it as a name for now. This mechanism is called phase kickback. And what we mean by phase kickback is that we encode information about our input in the phase of the combined result of input and output. No, I don't think they are mixed up a bit, but maybe you can give me a hint where you think that is the case, Tino. Actually, try to check this, and I also had others check it, so I'm pretty sure the math is sound, but maybe you can give me a hint. What 1 plus? This circle plus, yeah, 1 circle plus is plus then modulo 2. So it's 1 plus 1 is 0, because it's 1 plus 1 is 2, modulo 2 is 0, and 1 plus 0 is 1. That's what here. Yeah, UF is a gate, Tino. Or an operator, if you talk in quantum mechanics, but I didn't want to introduce operator here. But in the end, gates are similar or same thing as operators. Yeah, von X is just exactly 0 plus f of x is just f of x. Ah, okay, you mean this step here. Ah, okay, I didn't get that. Yeah, okay. That's right. You for 0 here, you basically use this term, so it's 0 plus modulo 2 f of x, and that's exactly f of x. Yeah. By here, you have to keep, here it's 1 plus f of x modulo 2 again. Then you think about what happens if you insert something actually, right? If the result is 0, this becomes simply 0, and this becomes simply 1, that is this one. And if you insert 1, this becomes 1. And this becomes 0 because it's modulo 2. And then it's 1 minus 0. And that you can write here. Okay? Okay. Good. Loose notation. Yeah, well, I mean, okay. Yeah. Maybe it's a bit too loose, but I think it should be okay with this like this. Very good. Now, what have we achieved? As I said, if there are not more questions. So what we have achieved is now, as I said, we have encoded this. We have encoded our information on the input, on the output in the input variable as a phase vector, basically. Now let's use that. In order to do that, we use another thing we have already seen. We put the input now in a superposition. So for the input, we also now just don't use one value, but we use a superposition of both possible input, again by this time using the 0 plus 1 mixed state. Okay? So we now just ignore this part here, because that stays constant. It's just the same as we piped it into our quantum circuit, and we just look at this part. So after application of this gate here, we get this part for the X. That's what I've written here, okay? This is just the input part, basically, with the encoded information on the function value, or function result. Now let's write this out. So we insert this one, and for the 0 state, this one would be -1 to the power of f of 0 times 0, and for this part here would be -1 to the power of f of 1 times 1. Let's think now what happens if we apply a constant function. For example, if we apply a function constant 0, then this one will give 1, and this one will give 1. Okay? And that's simply 0 plus 1. If we use constant -1, if we have a result of constant 1, this will be -1 and this will be -1. Okay? So it will be -0, -1 as a resulting state. You can put this in front and have again 1 over square root 2, 0 plus 1. A global phase, so a global sign which applies to the full qubit state of all qubits, can always be ignored if it squares to 1. So this -1 here can be ignored. So for constant qubit, for constant qubits, we get this result always. Now let's think what happens if we have a balanced version of the function. Then, for example, the result for identity of this one would be 0, because an identity 0 stays 0, and then the factor here would be 1. But here, for input 1, we would get output 1, and therefore this factor would -1 to the power of 1 be -1. So we get this function. And I don't want to repeat this now for the other way around, but again, you will see that despite this factor here of -1 for the full term, you will get this result. So, and that's now what Deutsch found out. For a constant function, you get always a different result in the first try, which you can discern from the result which you get from a balanced function, independently of how you actually form your balanced or your constant function. What we now can do in order to do a measurement on this, we use the reversibility of the H gate and transform this, which does transform this state again to the 1 state and this state again to the 0 state, measure it, and we know in 1, if our original function was balanced or constant. And that was indeed the first time where, or not the first time, but one of the first time where people could prove mathematically at least that a quantum computer would be always superior to a classical computer, at least from a complexity point of view. The good thing about this is, I mean, now we have 2 tries versus 1 try, but actually this algorithm can be extended to an arbitrary length of input, and it still can be solved in one run. So independently of how many bits you put in or many qubits you put in, you can always find out if it's balanced or constant with 1 try. While in the classical case, you would need 2 to the power of n minus 1 plus 1. You can think about it. It's quite simple. Why? Because you always have to try, in the worst case, at least half of your input values in order to find out if it's balanced or constant. So, yeah, that's Deutsche algorithm. And the first one which proves quantum superiority, at least for simple cases. And also one should say the Deutsche algorithm then, because it's a decision problem which can be mapped onto a lot of other problems, was the basis for a lot of further algorithms, like, for example, Shor's famous factorization, which then kickstarted the hype of quantum computing because it could break encryptions. He also started from this Deutsch problem and looked on how he could transform interesting issues into decision problems, which then could be matched to this idea. And the general idea is of Deutsch was, as I hopefully could point out, to use the power of quantum computing by using superpositions and entanglement in order to first achieve by entanglements, in order to first achieve by superposition this phase kickback, and then uses by entanglement in order to get the result in 1 try. Okay. Now, this has, as I feared, taken a bit longer than I would have hoped. So I'll say I leave this implementation of the Deutsche algorithm as a possible home exercise if you like to investigate this further. It's actually not so difficult. In order to do it, you need to prepare the 0 qubit in the 0 plus 1 state with the Hadamard gate. You need to prepare the output qubit in the 0 minus 1 state. You also know how that can be done. Then you need to apply an oracle, which you have to program, but I have provided a skeleton for this, which I will show briefly. And the oracle, you apply the Hadamard gate to qubit 0 and 1 and measure. And if you measure 0, 1, the function is constant. And if you measure 1, 1, it is balanced. Yeah, here are a few hints on how to implement this actually. And if you want to even go beyond that and want to have even more of a task ahead of you, you can also extend this to Deutsche Josa. It's actually quite simple. You just put more qubits into your circuit. You have to use a different oracle, of course, which kind of connects all qubits to the output and can therefore provide a balanced function. But then you can also do the same thing as in Deutsch, do the pre-processing by applying Hadamards and the X gate accordingly in order to put everything in the correct state. And then after the oracle, apply Hadamard gates to get the basis states and measure them. And if you measure 1, 0, 0, 0, it's a constant function. And if you measure something else, it's a balanced function. Okay, let me show. . the skeleton for this. Share my screen. Okay. We have an area here. It's the same as before. We import a little bit stuff. We use the chasm simulator again. We create a quantum circuit with 2 qubits. In this case, we separate our quantum circuits in 3 parts. And the first part is the pre-processing, which is here. And there you put the gates which you need to prepare the qubits before they get into the oracle. I have put a barrier function here which just beautifies a bit the output, because you will then see a barrier after the pre-processing, so you can optically visualize better the separation between the parts. Then there's another quantum circuit for the post-processing. There you do the Adamat gates in order to get everything into the basic states back again. Again, a barrier in the beginning this time in order to separate this from the oracle. And you put the instructions here, and then you implement the function or oracle, as I call it, or as it's called, either as a constant function or as a balanced function. I provided constant 1 here. If you, in order to get constant 1, you just put the output qubit to 1, right? So you just put a NOT gate right after the beginning of the quantum circuit onto the output qubit and set it to 1. And then it's a constant 1. It's output because it's independent of the input. If you want to do identity, you have to do something based on the input qubit, of course. And we only know 1 gate which can do something on the basis of the input qubit. And yeah, you have to make good use of that, and also do something else in combination with this gate in order to get the gate function implemented. Okay, then we combine everything into 1 quantum circuit and run it and measure it. Yeah, that's the task. But it's not enough time right now. So I just want to give the last 2 slides where I wanted to say a little bit about the state quantum computing is in. And that's typically called the noisy intermediate size quantum area, which is a term coined by John Preskill, who's one of the most known researchers in the area of quantum computing. He termed this noisy intermediate size quantum era. What does this mean? Noisy is because keeping qubits in these entangled and superposition states is a very tricky business. Interactions with the surroundings, like very small amounts of heat or other things, easily can change a qubit accidentally into another state, and this introduces, of course, errors into your quantum circuit. And this, in the end, results in noise in your results. So when you expect to only find, as before in Deutsche Algorithm, 1 state, you will also always find, if you measure often, other states as results, which are produced by this kind of noise and errors. Also, it's very tricky business to manipulate qubits. They are, as I said, very susceptible to interactions, and sometimes these gates we showed, like the C0 gate, do not result in the expected result, but do something else. That's another error source, basically. And yeah, well, that's why we call this era noisy. Intermediate size, we call it. We have right now quantum computers with 50 to 100 qubits. The expected amount of qubits needed in order to solve real-world problems is 1,000 to 1 million qubits. And we are still quite a far way away from that, of course. And that does mean in the current era, we just have to work with made-up examples, I would say, in order to research what can in the future be done with quantum computers. Yes, if a quantum computer has 10 qubits, you can only use a maximum of 10 qubits, that's true. In the future, of course, we want to make our quantum computers fault tolerant. And for this, there's much research in error correction. However, error correction needs a lot of additional qubits, so a lot of overhead. And our intermediate size quantum computers are just too small in order to achieve full fault tolerance. So we have to work with quantum computers which are not fully error tolerant, but only partly error corrected. All in all, this does mean currently there's no real world problem we can actually solve with a quantum computer. However, it's still a great time to do basic research in quantum computers because it offers such interesting topics at the border of mathematics, information science, and quantum mechanics. And it's really possible right now to understand the very basic workings of quantum algorithms, what probably will not be that easy once we get quantum computers with millions of qubits. So it's really now time to pave the way for new thinking about how information can be used in computations with qubits and in the quantum environment, I would say. Promising fields which have been identified for quantum computing are quantum chemistry, because you can, the best way to simulate a quantum system like a molecule is obviously to use a quantum computer, if it would be big enough, which it isn't, but once it's big enough, that's probably the only way to exactly calculate quantum systems. Another thing where there's much research is combinatorial optimization, so things like traveling salesmen. They are very well suited for quantum algorithms. And the field with much interest is also machine learning, even though that might also be just a hype topic. Okay, final slide. If you want to investigate this further, here are a few resources. For linear algebra, I can recommend this YouTube course here. Sorry, my voice is kind of failing. I was ill the last days. It's a very nice YouTube tutorial on linear algebra with some nice visualizations, which help a lot in order to get how these transformations work, etc. If this lecture of mine today was much too much math for you, there's also a guy from Microsoft who tried to explain Deutsche Algorithm with nearly no math at all, but instead using a state machine for the quantum computer. I'm not so sure if it's a good idea, because it's not that easy to extend it, but still it's an interesting watch. That would be this link here. Then there's a very nice blog article called Quantum Computing for the Very Curious. It's more involved than what I presented today, but I stole the title from them and just skipped the very, because very curious people should probably look into this blog article. If you want to know more about Qiskit, lots of tutorials are at Qiskit.org. They also have 2 textbooks in the meantime where they explore quantum computing with Jupyter notebooks. It's very nice to follow this. There's also good textbooks. The most famous and, in my opinion, best one is by Jack D. Hidary, An Applied Approach, Quantum Computing and Applied Approach. He has separated the maths in an extra chapter so you can digest it at your own speed, I would say, and try to change a bit between the quantum computing part and the math part, but it's all there and well explained. And then it's a German book, Quantum Computing Verstehen, if you prefer German. It's also very good by Matthias Hohmeister. It's also used in the lecture here of Professor Wag, as far as I know. And if you just want to get an overview on how the field is, of the state of quantum computer in the era of NISQ, noisy intermediate-sized quantum computers, John Preskill has written this in I would say, overview article with no intense knowledge required, which I have also linked here. Okay, so that concludes this last session for today. I hope, even though it was obviously a bit difficult and we had a few hurdles to take, that you got some idea of how quantum computing works and got interested to explore this further maybe. If you have any questions or want to talk about your solutions for the tasks we couldn't do today, just contact me. And yeah, otherwise, have a nice evening. I hope to see you around sometime. If you have still questions, I'll stay around for a couple of minutes, but I don't want to stop you from having your well-deserved evening activities.